Here is something to think about as you settle into tonight. Right now, in this very moment, there are billions upon billions of quantum events happening in the atoms that make up your body. Electrons are doing things that seem impossible. Light is behaving like both a wave and a particle simultaneously. Particles are existing in multiple states at once, and the act of paying attention to them changes their behavior. None of this makes intuitive sense, and yet it's not a mystery or an unsolved problem. We know this happens, we've measured it. We've built our entire technological civilization on top of these strange rules. But the story of how we came to understand this weirdness, the path from confusion to clarity, is itself one of the most beautiful narratives in human history. And that's what we're going to explore tonight, slowly, carefully, in a way that lets your mind wander if it needs to. Because the truth is, quantum physics isn't really about equations or mathematics at all, even though those matter. It's about how our understanding of the world shifted, brick by brick, from a picture that made sense to one that honestly still doesn't make complete sense, but works so perfectly that we've had to accept it anyway. And the people who made that shift, they weren't always comfortable with where it led them. Some of them spent their whole lives arguing against their own discoveries. Some found peace with the strangeness. Some never did. But all of them, in the end, had to face the same truth. The universe is far, far weirder than anyone expected. Let's start where reality started looking weird. And that's not actually with atoms or electrons or anything tiny. It starts with something you can experience yourself. Light. Specifically, what happens when you heat something up and it starts to glow. You know this phenomenon. You've seen it 1,000 times. Put a piece of metal in a flame, and as it gets hotter, it goes from black to dark red to bright orange to yellow, and if you push it hot enough, it becomes brilliant white. The color changes with the temperature, and by the late 1800s, physicists had measured this relationship extremely carefully. They could plot exactly how much energy a hot object releases at each color of the spectrum. They had beautiful experimental curves showing this relationship. Precise measurements that matched reality perfectly. But then they tried to explain these curves using the physics they had. The physics of Newton and Maxwell, the physics that had worked so well for so long. And they ran into a wall. A catastrophic wall. When the physicists did the math, following all the rules they knew, they got a prediction that was absolutely insane. Their equations said that as you move to higher frequencies of light, to violet and ultraviolet and beyond, the energy should just keep climbing toward infinity. It predicted that every warm object in the room should be blasting you with lethal ultraviolet radiation. Your coffee mug should be a death ray. Every warm thing should be dangerous. Obviously, that's not what happens. Your coffee mug is just warm. It doesn't kill you. So classical physics had a problem. A huge problem. And nobody knew how to fix it. That's where Max Planck comes in. And Planck is important, not because he was the most radical thinker of his time. He wasn't. He was actually quite conservative. He loved order and tradition and the foundations of physics as they existed. One of his mentors actually advised him against going into physics because the field was essentially complete. There was nothing important left to discover. And Planck seemed satisfied with that. He just wanted to understand what was already known more deeply. To polish the foundations rather than blow them up. But sometimes the universe has a sense of irony. Because in 1900, Planck was working on that black body radiation problem. And he found something interesting. He found a mathematical formula that matched the experimental data perfectly. The curve that showed how much energy was released at each frequency. His formula worked. It fit the observations. But here's the thing that bothered him. To make his formula work, he had to make an assumption that seemed physically wrong. He had to assume that energy isn't continuous the way he thought it was. Instead, he had to imagine that energy comes in tiny discrete packages, indivisible chunks, little grains of energy. He called these packets quanta, from the Latin word meaning how much or the amount. Now think about what this means. In everyday life, energy seems smooth. You can pour a little water into a cup or a lot of water, or any amount in between. Energy seemed like that too. You could have any amount you wanted. But Planck was saying no, energy is actually more like sand. Or like coins. You can have 1 penny or 2 pennies or 100 pennies, but you can't have 1 3/4 pennies. You can't have a fractional quantum of energy. The universe isn't divisible in that way. Planck himself didn't really believe this. He thought it was a mathematical trick, a clever accounting device that happened to give the right answer but wasn't actually describing reality. He spent years trying to find a way to explain the formula without this quantization assumption. He never succeeded. It haunted him. He called the introduction of quanta an act of desperation. He'd tried everything else and nothing worked. So he made this strange assumption. And it worked, and he never understood why. But he'd opened a door that couldn't be closed. The number Planck used to define the size of these quanta came to be called Planck's constant. It's an absurdly tiny number, 6.626 times 10 to the negative 34. That's a decimal point, followed by 33 zeros and then a 6. It's so small that in the everyday world you never notice the graininess. Water looks perfectly smooth even though it's made of molecules. The beach looks smooth from an airplane even though it's made of grains of sand. But at the atomic scale, Planck's constant matters. It changes everything. It's the fundamental scale at which the quantum world starts mattering. And in December 1900, Planck presented this idea to the German Physical Society. Nobody realized it, but he'd just lit a fuse that would take 25 years to fully explode. The person who picked up that fuse and ran with it was Albert Einstein. But not the Einstein you picture. In 1905, Einstein wasn't the elder statesman with the wild white hair. He was 26 years old. He couldn't get an academic job. He was working in a Swiss patent office as a technical expert, reviewing patent applications during the day and doing physics in his spare time. And in that one year, 1905, he published 4 papers that would each have made a career, one about relativity, one about atoms, and one that would win him a Nobel Prize. The photoelectric effect. Here's the puzzle Einstein was thinking about. When you shine light on certain metals, electrons pop off the surface. This had been observed experimentally. But here's what doesn't make sense according to classical physics. Light is a wave. Maxwell had proven that. And if light is a wave, then brighter light should knock electrons off with more energy. A bigger wave should do more damage. But that's not what happens. What actually happens is that the color of the light matters, not the brightness. Dim violet light can knock off high-energy electrons. Incredibly bright red light might knock off nothing at all. Brightness only changes how many electrons come off, not how energetic each one is. Classical physics couldn't explain it. Einstein's explanation was radical, and it was simple. He took Planck's idea about quantized energy and pushed it much further. He said that light itself comes in quanta. The light traveling through space doesn't just appear as quanta to matter. The light itself, traveling freely through empty space, exists as individual packets of energy, particles of light. We'd later call them photons, though that word wasn't invented until the 1920s. Each photon carries energy equal to Planck's constant times the frequency of the light. A violet photon carries more energy than a red photon because violet light has a higher frequency. When a photon hits an electron in the metal, it's a direct collision. 1 photon, 1 electron. If the photon carries enough energy to overcome the electron's binding to the metal, the electron pops free. Any leftover energy becomes the electron's kinetic energy, its speed. If the photon doesn't have enough energy, nothing happens. No matter how many red photons you throw at it, you can't do what 1 violet photon can do. 1,000,000 gentle taps can't do what 1 firm knock can. This was much bolder than what Planck had suggested. Planck had only quantized the oscillators in matter. Einstein was saying that light itself, that thing Maxwell had shown was a continuous wave, actually has a particle nature. It comes in lumps. And people didn't like it. Even Planck thought Einstein had gone too far. When Planck recommended Einstein for membership in the Prussian Academy of Sciences, he praised his work, but specifically noted that Einstein had sometimes gone astray, citing the light quantum hypothesis as an example. Planck was essentially saying great physicist, but the photon idea is probably wrong. But Einstein was right, and now you had something truly strange at the center of physics. Light is definitely a wave. The evidence for that was overwhelming. Interference patterns, diffraction, polarization, all wave phenomena. And yet Einstein showed it's also a particle. It comes in discrete chunks. Both things are true. Both things are confirmed by experiment. But how can something be both a wave and a particle? Those are opposite things. Those are contradictory. And yet the universe genuinely works this way. This contradiction is called wave-particle duality. And when you first encounter it, there's a natural urge to think that physicists must be confused, that they must be using language sloppily, that there's some misunderstanding. But there isn't. The universe really does work this way, and the discomfort you feel when you try to imagine it is exactly what the greatest physicists of the 1900s felt. And some of them never got comfortable with it. But they had to accept it anyway because the experiments demanded it. Meanwhile, there was another crisis brewing. And this one was about the atom itself. By the early 1900s, physicists knew atoms existed. They knew atoms contained electrons because J.J. Thomson had discovered the electron in 1897. But they had no idea how atoms were structured. Thomson's model imagined electrons embedded in a cloud of positive charge, like raisins in pudding. It seemed reasonable. But then, in 1909, Ernest Rutherford did an experiment that completely demolished that picture. Rutherford fired tiny, fast-moving particles at a thin sheet of gold foil. These particles were alpha particles, essentially helium nuclei, tiny, positively charged bullets. And something shocking happened. Most of them went straight through as expected. But some bounced at large angles, and a tiny fraction, a shocking handful, bounced almost straight back. They came back as if they'd hit something incredibly small, incredibly dense, and incredibly positively charged. Rutherford spent months working through the mathematics. And the conclusion was inescapable. Almost all of an atom's mass and all of its positive charge had to be concentrated in a fantastically tiny region at the center. He called it the nucleus. The numbers were staggering. The nucleus was something like 10,000 times smaller than the atom itself. If you scaled an atom up to the size of a football stadium, the nucleus would be a marble on the 50-yard line. Everything else, all that space where the electrons lived, was essentially empty. The solid world around you, the thing that feels firm and real and substantial, is overwhelmingly nothing. Your hand doesn't pass through the table not because atoms are solid, but because of electromagnetic forces between electrons. Forces that create barriers, even though the underlying structure is almost all empty space. Rutherford published his nuclear model in 1911, and it immediately explained the scattering data perfectly. But it had a fatal flaw, a devastating flaw. According to everything classical physics knew about electromagnetism, Rutherford's atom couldn't possibly exist. It should destroy itself almost instantly. Here's why. If you have a tiny, dense, positively charged nucleus at the center and negatively charged electrons somewhere around it, why don't the electrons just fall straight in? Opposite charges attract. The obvious answer is that the electrons are orbiting the nucleus, like planets orbiting the sun. The centripetal acceleration of their circular motion balances the inward pull of the electromagnetic force. They stay in stable orbits. It sounds perfectly reasonable. And that image, the little planetary atom, is probably what you grew up learning. But classical physics says it can't work. The problem is something called Larmor radiation. Maxwell's equations, the same beautiful equations that unified electricity and magnetism, those equations say very clearly that any charged particle that accelerates must radiate energy as electromagnetic waves. And an electron moving in a circle is constantly accelerating because its direction is constantly changing. Even if its speed stays the same, circular motion is acceleration. So a classically orbiting electron should be continuously radiating energy, losing energy, spiraling closer and closer to the nucleus. According to the calculations, an electron should spiral into the nucleus in about a 10 millionth of a second. The atom should collapse almost instantly. All atoms should have self-destructed long ago. Obviously they haven't. You're here. Chemistry works. Atoms are stable. So something was fundamentally wrong with the classical picture, and nobody knew what it was. This is where Niels Bohr comes in. And Bohr is one of the most fascinating figures in all of physics. He was Danish, born in Copenhagen in 1885. His father was a physiology professor. His mother came from a wealthy banking family. The household was deeply intellectual. Bohr and his younger brother Harold, who became a brilliant mathematician and also played for the Danish Olympic soccer team, that's a real fact. They grew up in an environment where serious ideas were discussed passionately. Niels was quiet, thoughtful, sometimes maddeningly slow to reach conclusions. But when he got there, he was usually right. He had a way of thinking that was almost geological. He'd turn a problem over and over, wearing it down from every angle. He'd express his ideas in language so careful and hedged with qualifications that sometimes people couldn't tell what he was saying. There's a famous story, possibly not true but telling, that when Bohr gave lectures, even other physicists would leave the room confused about what he'd actually claimed. But the ideas underneath all that careful language were revolutionary. In 1911, Bohr finished his doctorate and went to work with Rutherford in Manchester. And confronted with the impossible instability of Rutherford's atom, Bohr did something audacious. He didn't try to fix classical physics. He didn't look for some clever mechanism within Maxwell's equations that would stabilize the orbits. Instead, he said classical physics simply doesn't apply here. And then he made up new rules. In 1913, Bohr published his papers laying out what we now call the Bohr model of the atom. The key idea was this: electrons can only orbit the nucleus at certain specific distances, certain allowed orbits, and when they're in one of those orbits, they simply do not radiate energy. Not because there's some classical mechanism preventing it, but because that's how the quantum world works. It's a rule imposed from outside classical physics. The universe has rules that Maxwell didn't know about. Which orbits are allowed? Here's where Planck's constant shows up again. That same tiny number Planck introduced back in 1900. Bohr said the allowed orbits are the ones where the electron's angular momentum, a measure of its rotational motion, is a whole number multiple of Planck's constant divided by 2 pi. So the angular momentum can be 1 times that number, or 2 times it, or 3 times it. But never 1.5, never 2.7. The electron can be in the first allowed orbit, or the second, or the third, but never between them. It's quantized, discrete, lumpy. The electron doesn't smoothly spiral. It sits in one allowed orbit, stable, not radiating, until something happens to make it jump. And what happens when it jumps? Bohr said an electron can move from one allowed orbit to another, but when it does, it has to emit or absorb a very specific amount of energy, a quantum of energy equal to the difference between the energy levels of the 2 orbits. If it drops from a higher orbit to a lower one, it emits a photon, a particle of light whose energy exactly matches that difference. If it absorbs a photon with exactly the right energy, it jumps up. And because the orbits are discrete, the energy differences are discrete, which means the photons emitted or absorbed have very specific frequencies, very specific colors. And here's why that matters. For decades, physicists had known that when you heat a gas like hydrogen and look at the light it emits through a prism, you don't see a smooth rainbow. You see a series of sharp, bright lines at very specific wavelengths with darkness in between. These are called spectral lines. They're like a fingerprint for each element. In 1885, a Swiss schoolteacher named Johann Balmer had found a simple mathematical formula that predicted the wavelengths of the visible spectral lines of hydrogen with remarkable accuracy. But nobody knew why the formula worked. It was just a pattern, a numerical coincidence with no explanation. Bohr's model explained it. When he calculated the energy levels of his allowed orbits for hydrogen, and then calculated the frequencies of photons emitted when electrons jumped between those levels, the numbers matched Balmer's formula almost perfectly. Not approximately, not roughly, perfectly. The agreement was extraordinary. Bohr's model, with its strange quantum postulates, its defiance of classical electromagnetism, its seemingly arbitrary rules about allowed orbits, predicted the hydrogen spectrum with stunning precision. That's the thing about physics. You can propose the strangest, most counterintuitive theory you like, but if it predicts experimental results that nothing else can, people have to take it seriously. And they did. Bohr's 1913 papers caused a sensation. Einstein reportedly said something like, "This is one of the greatest discoveries." Rutherford was impressed but uneasy. He wrote to Bohr asking how the electron decides which orbit to jump to and when. It was a penetrating question. And Bohr didn't really have an answer. The model worked, but it felt incomplete. It felt like a set of rules handed down from somewhere. Rules that begged for a deeper explanation. Why these orbits? Why does the electron not radiate in them? What's the underlying mechanism? And there was a practical problem too. Bohr's model worked beautifully for hydrogen with its single electron. But when physicists tried to extend it to helium with 2 electrons, or to heavier elements, the model struggled. It couldn't accurately predict the spectral lines of more complex atoms. It was like having a key that opens one door perfectly but doesn't fit any others. Something deeper was needed. That deeper framework would take another decade to emerge. And when it did, it came from a generation of young physicists, many in their 20s, working with an intensity and creativity that's hard to believe. The period from roughly 1923 to 1927 is called the Golden Age of Quantum Physics, and the cast of characters reads like a novel. There's Werner Heisenberg, barely 23 years old, working on a North Sea island to escape his hay fever. There's Erwin Schrödinger, an Austrian with a complicated personal life who would derive his famous equation during a romantic holiday in the Swiss Alps. There's Paul Dirac, a quietly brilliant Englishman whose mathematical elegance reshaped the theory, Max Born and Wolfgang Pauli and Louis de Broglie, each contributing a piece of the puzzle. But before any of them could build the full framework, one more crucial idea had to come into play. And it started with a French prince with an unusual question about electrons and waves. Louis de Broglie came from an aristocratic family prominent in French politics and military affairs for centuries. He actually held the title of prince. He'd originally studied history at the Sorbonne, planning a career in humanities. But his older brother Maurice was a physicist working on X-rays. Something about the family dinner table conversations pulled Louis in. He switched to physics, and by 1923 he was working on his doctoral thesis, turning over a question again and again in his mind. If light, which everyone treated as a wave, could also behave like a particle, which Einstein had shown with photons, shouldn't the reverse also be true? Shouldn't matter, which everyone treated as particles, also behave like waves? Think about how audacious that is. An electron, a tiny speck of stuff with mass and charge. Something you can deflect with a magnet. Something that leaves tracks in cloud chambers. De Broglie was suggesting that this thing also has a wavelength. It ripples. It diffracts and interferes, just like light passing through double slits. And he didn't suggest it vaguely. He wrote down a formula. The wavelength of any particle equals Planck's constant divided by the particle's momentum. Lambda equals h over p. And notice what's sitting right there in the equation. Planck's constant again. That same tiny number Planck introduced as a mathematical trick back in 1900, and that Bohr used to define his allowed orbits. It keeps showing up like a thread running through the whole story. Now the wavelength you get from de Broglie's formula depends on the momentum of the particle. And momentum is mass times velocity. For anything you can hold in your hand, a baseball, a grain of sand, even a bacterium, the mass is so enormous compared to Planck's constant that the wavelength comes out absurdly small, trillions of times smaller than an atomic nucleus. You'd never notice it. That's why the everyday world doesn't seem wavy. But for something as light as an electron, the wavelength turns out to be on the order of the size of an atom. And that changes everything. Here's why. Remember how Bohr's model had this rule that electrons could only occupy certain orbits, certain specific distances from the nucleus, and nobody could explain why. It was just a postulate, a rule imposed from outside to make the math work. De Broglie's idea gave it a physical explanation. If an electron is a wave, and it's traveling around the nucleus in a circular orbit, then that wave has to connect back up with itself after going all the way around. It has to form what's called a standing wave. Think of a guitar string. When you pluck it, it vibrates. But it can only vibrate in certain patterns. The fundamental note, the first harmonic, the second harmonic. It can't vibrate in just any arbitrary shape because the ends are fixed. The wave has to fit. The same principle applies to an electron wave wrapped around a nucleus. The circumference of the orbit has to be a whole number of wavelengths. 1 wavelength, 2 wavelengths, 3, 4. But not 1.5, not 2 3/4. If the wave doesn't fit, it interferes with itself destructively and cancels out. It can't exist in that orbit. And when you work out the math, the orbits where the wave does fit are exactly the orbits Bohr had postulated. The quantization of electron orbits isn't some mysterious decree from on high. It's a natural consequence of electrons being waves. It's the same reason a flute can only play certain notes. De Broglie presented this idea in his doctoral thesis in 1924. The story goes that his thesis committee wasn't entirely sure what to make of it. It was elegant. It was bold. But it was also a claim that everything made of matter is also a wave. And that's not the kind of thing you just nod along with. One of the examiners sent the thesis to Einstein for a second opinion. Einstein reportedly replied that de Broglie had lifted a corner of the Great Veil. That was enough. The thesis was accepted, and de Broglie eventually won the Nobel Prize for it in 1929. And here's the thing. His prediction was experimentally confirmed. In 1927, Clinton Davison and Lester Germer, working at Bell Labs in New York, fired electrons at a nickel crystal and observed a diffraction pattern. The electrons were behaving exactly like waves, scattering off the regularly spaced atoms in the crystal the same way X-rays scatter off crystal planes. Independently, George P. Thomson showed electron diffraction through thin metal films. And yes, he was the son of J.J. Thomson, the man who discovered the electron as a particle. Father discovers the electron as a particle. Son shows it's a wave. Both won Nobel Prizes. Both were right. That's quantum physics for you. So by the mid-1920s, the pieces were accumulating. Energy is quantized. Light is both wave and particle. Electrons are both wave and particle. Bohr's atom works for hydrogen, but not for anything more complicated. And there's this growing sense in the physics community that what's needed isn't another patch. What's needed is a completely new mathematical framework, a new mechanics, something to replace Newton's laws at the atomic scale the way Einstein's relativity had replaced them at high speeds and strong gravity. And in 1925 and 1926, that framework arrived almost simultaneously from two completely different directions. The first came from Werner Heisenberg. And the story of how he got there is one of those beautiful accidents that history occasionally provides. In the summer of 1925, Heisenberg was 23 years old, working as an assistant to Max Born in Göttingen. He was brilliant, impatient, and suffering terribly from hay fever. The pollen was so bad he could barely think. So he asked for leave and took a ferry to Helgoland, a tiny rocky island in the North Sea, where there was almost no vegetation and, crucially, almost no pollen. And there, alone on this windswept island, he worked through the nights on a radical idea. Heisenberg's approach was to throw out everything you couldn't directly observe. You can't see an electron orbiting a nucleus. You can't watch it trace a path. What you can observe are the frequencies and intensities of the light atoms emit and absorb. They're spectral lines. So Heisenberg decided to build a theory entirely out of observable quantities. He constructed mathematical tables, arrays of numbers that described the relationships between different energy states of an atom and the probabilities of transitions between them. He wasn't thinking about where the electron was or what path it followed. He was thinking only about what you could measure. The math he ended up with was strange. When he multiplied two of his tables together, the result depended on the order of multiplication. A times B did not equal B times A. In ordinary arithmetic, 3 times 5 is the same as 5 times 3. But Heisenberg's quantities didn't work that way. He found this deeply unsettling. He later said he was so disturbed by it that he stayed up all night checking his calculations. And at 3 in the morning, when he'd confirmed the result, he was too excited to sleep and walked out to the tip of the island to watch the sun rise over the sea. He knew he had something, even if he didn't fully understand what it was. When he brought the work back to Göttingen, Max Born looked at it and recognized the mathematical structure immediately. Heisenberg had reinvented matrix algebra. The tables of numbers were matrices, and the fact that their multiplication isn't commutative, that the order matters, is a fundamental property of matrices. Born, together with his student Pascual Jordan, helped Heisenberg formalize the theory into what became known as matrix mechanics. It was the first complete, self-consistent formulation of quantum mechanics. And it worked. It could predict the spectral lines of hydrogen. It could handle more complex atoms, too. But it was also almost impenetrably abstract. Most physicists at the time found it very difficult to work with. There was no picture of what was happening, no visualization. Just these arrays of numbers and algebraic rules. It felt like pure mathematics with no physical intuition to hold on to. And then just a few months later, in early 1926, Erwin Schrödinger published a completely different approach. Schrödinger was in his late 30s, older than most of the other quantum revolutionaries, and he was inspired directly by de Broglie's idea of matter waves. If electrons are waves, Schrödinger reasoned, then there should be a wave equation that governs them. Just as Maxwell's equations govern electromagnetic waves, and the classical wave equation governs vibrations on a string. So he set out to find it. The circumstances of the discovery have become legendary and a little scandalous. In December 1925, Schrödinger went on a holiday to a villa in Arosa in the Swiss Alps. He brought along a woman who was not his wife. History has never conclusively established who she was, but it was a love affair. And during this retreat, over the course of a few intensely productive weeks, he derived the equation that now bears his name, the Schrödinger equation. It describes how a mathematical object called the wave function evolves over time, and the wave function, usually written with the Greek letter psi, contains in principle everything you can know about a quantum system. Now, the Schrödinger equation looked much more familiar to physicists than Heisenberg's matrices. It was a differential equation, the kind of math physicists had been using for centuries to describe fluids and heat and vibrations. You could picture things. You could imagine the wave function as a real wave sloshing around in space. Schrödinger himself believed, at least initially, that the wave function was a physically real thing, that the electron literally was a wave smeared out in space. And the wave function described its shape. Physicists loved it, it was intuitive, it was powerful. And it gave the same answers as Heisenberg's matrix mechanics for every problem anyone tried. So now there were two apparently different theories of quantum mechanics, both giving the same predictions. And a natural question arose. Were they really different, or were they the same theory in disguise? Schrödinger himself showed in 1926 that the two formulations were mathematically equivalent. Matrix mechanics and wave mechanics were just two different languages for describing the same underlying physics. the way you can describe a circle with Cartesian coordinates or polar coordinates. Same shape, different notation. Later, Paul Dirac would unify both into an even more general and elegant framework. But that's a story for later. The more immediate question, the one that would consume physics for years and is honestly still debated today, was about interpretation. What does the wave function actually mean? What is it telling us about reality? Schrödinger thought it described a real physical wave. But there was a problem with that picture. Max Born pointed it out. Born noted that when you solve the Schrödinger equation for, say, an electron in an atom, the wave function spreads out over a region of space. It doesn't sit at a single point. But when you actually measure the electron's position, you always find it at a specific location. You never detect half an electron here and half an electron there. So the wave function can't literally be the electron smeared out. Instead, Born proposed something more subtle and frankly more disturbing. He said the wave function gives you probabilities. Specifically, the square of the wave function at any point in space tells you the probability of finding the electron at that point. If you make a measurement, the electron isn't smeared out. Your knowledge of where it is smeared out. Before you measure, the wave function describes a cloud of possibilities. After you measure, you get a definite result, and the wave function collapses to a single point. This was a profound shift. For the first time in the history of physics, a fundamental theory was saying that nature is at its deepest level probabilistic. Not because we lack information, not because our instruments aren't good enough, but inherently, fundamentally random. And this idea, this probabilistic interpretation, would become one of the central pillars of what's called the Copenhagen interpretation of quantum mechanics, championed by Bohr and Heisenberg. But not everyone was comfortable with it, not even close. And the person who objected most famously, most persistently, and most eloquently was someone you've already met in this story. The same man who had started the whole quantum revolution with his paper on the photoelectric effect. And the debate between Einstein and Bohr over the meaning of quantum mechanics would become one of the most celebrated intellectual battles in the history of science. It wasn't a petty squabble, it wasn't ego, though both men had plenty of that. It was a genuine, deeply felt disagreement about what reality is, what physics is supposed to do, and whether the universe, at its most fundamental level, is knowable in the way that physicists had always assumed it was. Let's set the stage. By the late 1920s, quantum mechanics worked. It worked spectacularly well. You could use Schrödinger's equation to predict the energy levels of atoms, the behavior of molecules, the way light interacted with matter. The math gave you numbers, and those numbers matched experiments to extraordinary precision. Nobody disputed that. What Einstein disputed was what the math meant. And this distinction matters because in physics, having equations that give correct predictions is not the same as understanding what's going on. You can have a recipe that makes a perfect cake every time and still have no idea why those particular ingredients in those particular proportions produce that result. Einstein wanted to know why. He wanted to know what was really happening when you weren't looking. Here's the thing about the Copenhagen interpretation, the view championed by Bohr and Heisenberg. It essentially said, don't ask that question. Or more precisely, it said, the question doesn't have a meaningful answer. According to Copenhagen, the wave function is the most complete description of a quantum system that's possible. There's no deeper layer underneath. When you ask, where is the electron before I measure it, Copenhagen says the electron doesn't have a definite position before you measure it. It's not that you don't know where it is, it's that there's genuinely no fact of the matter about where it is until the measurement happens. The measurement doesn't reveal a pre-existing reality. It creates the reality. And if you're thinking that sounds bizarre, you're in excellent company. Einstein thought it was bizarre too. Not because he couldn't follow the math. He could follow the math better than almost anyone alive. But because it offended something deep in his physical intuition. He believed that particles have definite properties, whether or not anyone is looking at them. He believed that the moon is there even when nobody is observing it. He once actually said something very close to that, asking a colleague whether he really believed the moon exists only when he looks at it. That wasn't a frivolous question. It was getting at the heart of what Copenhagen seemed to imply. So the debates began, playing out most dramatically at a series of conferences in Brussels. These were invitation-only gatherings of the world's top physicists funded by the Belgian industrialist Ernest Solvay. And they were extraordinary events. The 1927 Solvay Conference is particularly famous. There's a photograph from it that you've probably seen even if you didn't know what it was. Rows of serious-looking men in suits. And among them are Einstein, Bohr, Heisenberg, Schrödinger, Dirac, Born, Planck, de Broglie, Lorentz, Marie Curie, and about a dozen others. 17 of the 29 attendees were or would become Nobel laureates. It's arguably the most impressive group photo in the history of human thought. And at that conference, Einstein began his campaign against the Copenhagen interpretation. His strategy was clever. He didn't try to prove the math wrong. He knew the math worked. Instead, he constructed thought experiments, hypothetical scenarios designed to show that quantum mechanics was incomplete, that it couldn't be the whole story, that there must be some deeper deterministic theory underneath that would restore the certainty and definiteness that classical physics had always provided. At breakfast, Einstein would present Bohr with a new thought experiment, some ingenious setup involving slits and screens and shutters and clocks, designed to show that you could, in principle, simultaneously know both the position and the momentum of a particle with arbitrary precision, which would violate Heisenberg's uncertainty principle. And Bohr would spend the day agonizing over it, pacing, muttering, working through the logic. And by dinner, Bohr would have found the flaw. Every time. Einstein would construct a beautiful trap, and Bohr would find the hidden escape hatch. One of the most famous examples came at the 1930 Solvay Conference 3 years later. Einstein proposed a thought experiment involving a box filled with radiation. The box had a clock-controlled shutter that opens for a precisely known interval, letting out a single photon. You weigh the box before and after, using Einstein's own equation, E equals mc squared, to determine the energy of the escaped photon from the tiny change in mass. Since you know exactly when the shutter opened and exactly how much energy left, you'd know both the time and the energy of the photon precisely, violating the energy-time version of the uncertainty principle. This one actually shook Bohr. Reportedly, he was quite distressed that evening. He couldn't immediately see the flaw. But by the next morning, he had found it. And here's the beautiful irony. He used Einstein's own general theory of relativity to do it. Bohr pointed out that when you weigh the box, it moves slightly in the gravitational field. And according to general relativity, a clock that moves in a gravitational field experiences time dilation. That tiny shift in the box's position introduces an unavoidable uncertainty in the timing of the shutter's opening. When you work through the math carefully, this gravitational time dilation introduces exactly enough uncertainty to preserve Heisenberg's principle. Einstein had been defeated by his own theory. Think about what that means. Einstein, arguably the greatest physicist who ever lived, spent years trying to find a logical contradiction in quantum mechanics. And he couldn't do it. That doesn't prove quantum mechanics is right in some ultimate philosophical sense. But it does tell you something about how robust the framework is. It resists even the most brilliant attacks. But Einstein didn't give up. He just changed tactics. By the mid-1930s, he stopped trying to show that quantum mechanics was logically inconsistent, and instead tried to show that it was incomplete, that it was missing something. And this led to one of the most famous papers in the history of physics. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a paper universally known by their initials, EPR. The title was, "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" And the answer they argued for was no. Here's the setup, simplified a bit from their original version. Imagine you have a source that produces two particles that fly off in opposite directions. These particles are created in a way that their properties are correlated. Quantum mechanics calls this entanglement, a term that Schrödinger actually coined that same year, calling it the characteristic trait of quantum mechanics. Say the particles are correlated so that if you measure one and find it spinning clockwise, the other must be spinning counterclockwise. Quantum mechanics predicts this correlation, and it's been confirmed experimentally countless times. Now, here's the EPR argument. According to Copenhagen, neither particle has a definite spin direction until you measure it. The spin is genuinely undetermined. But the moment you measure particle A and find it spinning clockwise, you instantly know that particle B is spinning counterclockwise. Even if particle B is on the other side of the galaxy, how does particle B know what result particle A got? How does the information get there? If it happens instantaneously, it would violate special relativity, which says nothing can travel faster than light. Einstein called this spooky action at a distance, and he meant it dismissively. He thought it was absurd. The much simpler explanation, he argued, was that both particles had definite spin directions all along, from the moment they were created. Quantum mechanics just didn't capture that information. It was like a pair of gloves. If you find the left glove in one box, you instantly know the right glove is in the other box. No spooky action required. The gloves were always left and right, you just didn't know which was which until you looked. This is what's called a local hidden variables theory. Local meaning no faster than light influences. Hidden variables meaning there are definite properties that exist but that quantum mechanics doesn't describe. Einstein believed something like this had to be true. The EPR paper was his strongest, most carefully constructed argument. And it genuinely troubled Bohr. Bohr's response, published later that year, was long and somewhat convoluted. And honestly, many physicists at the time found it less than fully convincing. The EPR argument lingered. It didn't go away. And here's what's remarkable. It didn't get resolved for nearly 30 years. The EPR paper was published in 1935. And for decades, it was considered more of a philosophical puzzle than a scientific one. Most working physicists shrugged and got on with using quantum mechanics to build things and predict things. The interpretation debates were seen as almost a matter of taste. You could be a Copenhagen person or an Einstein person. It didn't affect your calculations either way. The equations were the same regardless of what you believed was really going on underneath. But then in 1964, an Irish physicist named John Stuart Bell changed everything. Bell was working at CERN, the European Particle Physics Laboratory in Geneva. And he had been quietly thinking about the EPR argument for years. What Bell did was extraordinary in its simplicity. He asked a question that nobody had thought to ask, or at least nobody had figured out how to answer. Is there actually an experimental difference between quantum mechanics and any possible local hidden variables theory? Can you design a test that would give different results depending on which view is correct? And the answer, astonishingly, was yes. Bell derived a mathematical inequality now called Bell's inequality that any local hidden variables theory must satisfy. Think of it like a speed limit. If the universe works the way Einstein hoped, with particles carrying definite hidden properties and no faster than light influences, then certain statistical correlations between measurements on entangled particles can never exceed a particular value. It's a ceiling, a boundary. But quantum mechanics predicts that in certain experimental setups, that ceiling will be violated. The correlations will be stronger than any local hidden variables theory can possibly produce. This was no longer philosophy. This was a concrete, testable prediction. You could actually go into a laboratory, produce entangled particles, make measurements, tally up the statistics, and check whether Bell's inequality holds or is violated. And starting in the 1970s, physicists began doing exactly that. The most famous early experiments were conducted by Alain Aspect and his team at the University of Paris-Sud in Orsay, France, in 1981 and 1982. Aspect's experiments were ingenious in their design. He used pairs of entangled photons produced by exciting calcium atoms. And he measured their polarizations along different angles. Crucially, he included a feature that addressed one of the biggest loopholes. He used rapid switching of the measurement settings while the photons were already in flight, so that neither photon could possibly know what measurement the other one would face. There was no time for any signal, even one traveling at the speed of light, to pass between them. The results were unambiguous. Bell's inequality was violated. The correlations were exactly what quantum mechanics predicted, and they were stronger than any local hidden variables theory could explain. Einstein's hope that particles carry definite properties all along, and that quantum mechanics is just an incomplete description of a deeper, sensible, deterministic reality, was experimentally ruled out, at least in its simplest form. Now let me be careful here, because this is subtle, and it matters. What Bell's theorem and aspects experiments rule out is the combination of locality and hidden variables together. You can still have hidden variables if you're willing to give up locality, if you accept that influences can travel faster than light. David Bohm actually developed a fully deterministic interpretation of quantum mechanics along exactly those lines back in 1952. And it reproduces all the predictions of standard quantum mechanics perfectly. But it requires a kind of instantaneous non-local connection between distant particles, which many physicists find deeply uncomfortable. Or you can keep locality and give up hidden variables, which is essentially what Copenhagen does. What you can't do, and this is Bell's great contribution, is keep both. The experiments have only gotten more precise since Aspect's pioneering work. In 2015, a team led by Ronald Hansen at Delft University of Technology in the Netherlands performed what's considered the first truly loophole-free Bell test, closing all the major experimental gaps simultaneously. The result was the same. Quantum mechanics wins. Nature really is as strange as the theory says. Now here's something to sit with as you're drifting. The implications of all this for how we understand technology and reality are profound. Because once you accept that quantum mechanics is telling you something true about the world, that particles don't have definite properties until measured, that entanglement creates correlations that can't be explained classically, that probability is woven into the fabric of reality, you start wondering what else this theory implies. And one of the strangest, most counterintuitive, and most practically important implications has to do with what happens when you take quantum mechanics and apply it not to single particles flying through space, but to huge collections of particles packed together in a solid material. Because that's where you get into the quantum physics of matter itself, the behavior of electrons inside metals and semiconductors and insulators. And that's where quantum mechanics stops being an abstract debate between geniuses in Brussels and starts becoming the reason you have a phone in your pocket and a computer on your desk. Start with a simple question. You've got a chunk of copper. It conducts electricity. You've got a chunk of rubber. It doesn't. Why? That seems like it should have a straightforward answer. And for a long time, people kind of hand-waved their way through it. They said something like, well, copper has free electrons that can move around and rubber doesn't, which is true as far as it goes. But it doesn't really explain anything. Why are those electrons free? What makes copper different from rubber at the atomic level? Classical physics couldn't give you a satisfying answer. It could describe the behavior. This material conducts, that one insulates. But it couldn't explain the mechanism from first principles. Quantum mechanics can. And the way it does it is through one of the most elegant ideas in all of physics, something called band theory. But before we get there, we need to talk about a principle that might be the most important rule in quantum mechanics that nobody outside of physics has heard of. It's called the Pauli exclusion principle, and it was proposed in 1925 by a young Austrian physicist named Wolfgang Pauli. Pauli is one of those characters who deserves a moment. He was brilliant. Genuinely one of the sharpest minds in 20th century physics. But he was also famously sharp-tongued. He had a reputation for being brutally critical. There's a famous story, probably embellished but telling, that Pauli once dismissed a colleague's paper by saying it's not even wrong. Meaning the paper was so confused it didn't even rise to the level of being incorrect. That's the kind of guy Pauli was. He didn't suffer fools, and his standards were impossibly high, including for himself. But in 1925, Pauli was wrestling with a real puzzle. Physicists had been trying to understand the structure of atoms. How do electrons arrange themselves around the nucleus? Bohr's model gave you these quantized orbits, these energy levels. That was great. It explained a lot about hydrogen. But when you tried to apply it to bigger atoms, atoms with lots of electrons, things got complicated. Why did electrons fill up the energy levels the way they did? Why didn't all the electrons in an atom just pile into the lowest energy level, the ground state, and sit there? That would be the lowest energy configuration. So classically, that's what you'd expect. But atoms don't work that way. Electrons seem to spread themselves out across different energy levels in a very specific pattern. And that pattern is what gives each element its chemical properties. Pauli's insight was deceptively simple. He proposed that no two electrons in an atom can occupy the exact same quantum state at the same time. That's it. That's the exclusion principle. Two electrons can share the same energy level, but only if they differ in at least one quantum property, specifically their spin, which is this intrinsic angular momentum that electrons carry, and which can point in one of two directions, up or down. So each energy level can hold at most two electrons, one spin up and one spin down, and after that the next electron has to go to a higher energy level. Think about what that means. It means electrons are forced to stack up layer by layer into higher and higher energy states. Not because they're being pushed there by some force, but because the rules of quantum mechanics simply forbid them from all crowding into the same state. It's like a cosmic game of musical chairs where every chair can only hold two players, and once it's full, you have to find the next chair up. This one rule, this exclusion principle, explains the entire periodic table. It explains why atoms have the chemical properties they do, why elements in the same column of the periodic table behave similarly, why noble gases are inert, why alkali metals are reactive. All of it traces back to how electrons are forced to fill up quantum states according to Pauli's rule. Now here's where it gets really interesting. Take that idea, electrons filling up states from the bottom, two per state, and instead of thinking about a single atom, think about a solid. A crystal of silicon, say, or a wire made of copper. You've got billions and billions of atoms packed together in a regular lattice. And each atom is contributing its electrons to the collective pool. What happens to the energy levels in a single atom? The energy levels are sharp and discrete. An electron can be in this state or that state, but nothing in between. But when you bring atoms close together, really close, the way they are in a solid, something beautiful happens. The energy levels of neighboring atoms start to interact with each other. They overlap, and because of quantum mechanics, those sharp, discrete levels spread out into broad bands of allowed energies. It's like this. If a single atom has one specific note it can play, like a single frequency on a piano, then a solid made of trillions of atoms has those notes smeared out into a continuous chord. Each sharp energy level becomes a wide band containing an enormous number of very closely spaced states. And between these bands, there can be gaps. Ranges of energy where no electron states exist at all. These are called band gaps. And they turn out to be the key to everything. Here's the picture. In any solid, you've got these bands of allowed electron energies, separated by gaps of forbidden energies. The electrons fill up the bands from the bottom, following Pauli's exclusion principle. Two per state. The highest band that's got electrons in it at absolute zero temperature is called the valence band. The next band up, which might be empty or partially filled, is called the conduction band. And the gap between them, the band gap, determines whether the material is a conductor, an insulator, or a semiconductor, if there's no gap at all. If the valence band and the conduction band overlap, or if the valence band is only partially filled, then electrons can easily move into higher energy states and flow through the material when you apply a voltage. That's a conductor. That's copper. The electrons at the top of the filled states barely need any energy to start moving, so current flows freely. If the gap is very large, say 8 or 9 electron volts like in diamond, then electrons in the valence band are stuck. They can't jump across that huge gap to reach the conduction band, at least not at normal temperatures. No mobile electrons. No current. That's an insulator. But here's the thing. What if the gap is small? What if it's just a little gap? Maybe 1 electron volt. Maybe a little more. That's a semiconductor. And semiconductors are where the magic happens. At absolute zero, a semiconductor behaves like an insulator. The valence band is full, the conduction band is empty, and the gap prevents current flow. But at room temperature, there's enough thermal energy bouncing around that some electrons can jump across that small gap into the conduction band. Not a lot of them, but some. And those few mobile electrons can carry a current. Silicon has a band gap of about 1.1 electron volts. Germanium is about 0.67. These numbers matter enormously because they determine how the material behaves at different temperatures and how it responds to light and electric fields. Now, this is already pretty remarkable. Quantum mechanics explaining why some materials conduct and others don't. All from first principles. But the story of semiconductors gets much richer when you start deliberately modifying them. And this is where we get to one of the most consequential engineering ideas of the 20th century. Doping. Doping is when you intentionally introduce tiny amounts of impure atoms into a semiconductor crystal. And by tiny, I mean tiny. Maybe 1 impure atom for every million silicon atoms. But that small contamination changes everything. Say you take pure silicon. Each silicon atom has 4 outer electrons, and in the crystal, each atom shares those 4 electrons with its 4 neighbors in neat covalent bonds. Everything is tidy. Everything is paired up, and at low temperatures there are no free electrons to carry current. Now replace 1 silicon atom with a phosphorus atom. Phosphorus has 5 outer electrons. 4 of them fit neatly into the bonding structure just like silicon's. But that 5th electron has nowhere to go. It's loosely bound, and at room temperature it breaks free and becomes a mobile charge carrier. You've just created an N-type semiconductor. N for negative because the free carriers are electrons. Now do the opposite. Replace a silicon atom with a boron atom. Boron has only 3 outer electrons. It can fill 3 of the 4 bonds. But the 4th bond has a hole. A missing electron. That hole behaves in a wonderfully strange quantum mechanical way, like a positive charge carrier. It can move through the crystal as neighboring electrons shuffle around to fill it, creating a new hole somewhere else. It's like that sliding tile puzzle you might have played with as a kid. The empty space moves around even though it's the tiles that are actually sliding. An electron fills the hole, leaving a new hole behind, and the hole effectively travels through the material. This is a p-type semiconductor, P for positive. And here's where it gets really clever. Take a piece of N-type silicon and put it right next to a piece of p-type silicon. What you get is called a p-n junction. And it's the fundamental building block of nearly all modern electronics. At that junction, something fascinating happens. The extra electrons from the N side start diffusing across into the P side, and the holes from the P side start diffusing into the N side. But as they cross over, they leave behind charged atoms. The phosphorus atoms on the N side become positively charged because they've lost their extra electron. And the boron atoms on the P side become negatively charged because they've gained one. This creates an electric field right at the junction. A built-in voltage that opposes further diffusion. It's a self-regulating process. The diffusion creates the field, and the field stops the diffusion. You end up with a thin region at the junction called the depletion zone, where there are very few free carriers. This little region, this depletion zone in a p-n junction, is the heart of the diode, the transistor, the solar cell, the LED. It's the reason your phone works. It's the reason computers exist. It's the reason we can convert sunlight into electricity. all from quantum mechanics, all from Pauli's exclusion principle and band theory, and the careful manipulation of band gaps through doping. The person who really put all of this together into a working transistor was William Shockley, the device that replaced vacuum tubes and launched the information age. That's a story with some drama in it. It happened at Bell Labs in Murray Hill, New Jersey in the late 1940s. And it involved three physicists whose collaboration was brilliant and whose personal dynamics were complicated. Their names were William Shockley, John Bardeen, and Walter Brattain. And the story of how they invented the transistor and what happened afterward is one of the great tales of 20th century engineering. Shockley was the group leader. Ambitious, driven, absolutely convinced that semiconductors were the future. He'd been thinking about semiconductor amplifiers since before the war. Bardeen was the theorist. Quiet, deep. A man who would go on to win 2 Nobel Prizes in physics. The only person ever to do that. And Brattain was the experimentalist. The guy with the steady hands and the intuition for making things actually work in the lab. Together they were formidable. But the dynamics between them, especially between Shockley and the other two, were about to get really messy. Here's what happened. Shockley had this idea for a field effect transistor, a device where you'd use an electric field to control the flow of current through a semiconductor. He'd sketched it out. He'd done the calculations. And on paper it should have worked. But when Brattain tried to build it, nothing happened. The semiconductor just sat there. No amplification. No switching. Nothing. And Shockley couldn't figure out why. That's when Bardeen stepped in with one of those quiet, devastating insights that only a truly deep thinker can produce. He proposed that there were surface states. Electrons getting trapped at the surface of the semiconductor, forming a shield that was blocking Shockley's external field from penetrating into the material. The field was being screened out before it could do anything useful. It was a subtle quantum mechanical effect. And it explained perfectly why Shockley's design wasn't working. And here's where the interpersonal dynamics start to matter, because Shockley took this as a personal failure. His idea hadn't worked. Bardeen had figured out why. And from that point on, Shockley began to pull back from the day-to-day collaboration, nursing what seems to have been a bruised ego. So Bardeen and Brattain started working together more closely. Just the two of them, trying to find a way around the surface state problem. And in December of 1947, they did something remarkable. They built a device that was crude, almost laughably crude by modern standards. Brattain took a small slab of germanium, not silicon, germanium, which was the semiconductor of choice at the time, and he pressed 2 gold contacts into its surface. Very close together, separated by just a tiny fraction of an inch. He had actually taken a plastic triangle, wrapped gold foil around it, and then carefully cut a slit in the foil at the point of the triangle with a razor blade, creating 2 contacts separated by maybe 50 thousandths of an inch. It looked like something you'd build in a garage. But when they applied a small current to one of those gold contacts, they found they could control a much larger current flowing through the other one. Amplification. A tiny signal in, a bigger signal out. The first working transistor. They called it the point contact transistor. And it worked. On December 23, 1947, Brattain's lab notebook from that day still exists. He wrote down the results, noted the power gain, and his supervisor signed the page as a witness. It's one of those moments in technology history that you can point to and say, right there, that's when the future changed. Everything that came after. Every computer, every smartphone, every satellite, every piece of the internet traces back to that little triangle of plastic with gold foil on a slab of germanium. But here's the human part that makes this story sting. When Shockley found out what Bardeen and Brattain had achieved, he was furious. Not because it didn't work, because it did. And he hadn't been in the room, he hadn't been part of the breakthrough. His name wouldn't be on the patent for the point contact transistor. And for a man as ambitious and ego-driven as William Shockley, that was intolerable. So Shockley did something that was either incredibly petty or incredibly brilliant, depending on how you look at it. Maybe both. He went off on his own over New Year, holed up in a hotel room in Chicago, and in a burst of concentrated work, he invented a completely different and ultimately better type of transistor. The junction transistor. Instead of using two-point contacts pressed against a surface, Shockley's design used a sandwich of semiconductor material, N-type, then P-type, then N-type again, or PNP, 3 layers. By controlling the current flowing into the thin middle layer, the base, you could control a much larger current flowing between the outer 2 layers. It was more robust, more reliable, easier to manufacture, and it's the basic architecture that would go on to dominate the industry. So in a way, Shockley's wounded pride produced a better transistor, but it also poisoned the working relationship permanently. When the Nobel Prize in Physics was awarded in 1956, all 3 men shared it, Shockley, Bardeen, and Brattain. But by then they were barely speaking. Bardeen had left Bell Labs for the University of Illinois, where he'd go on to do foundational work on superconductivity and win his second Nobel. Brattain continued his research quietly, and Shockley went to California. And this is where the story takes a turn that shapes the modern world in ways that have nothing to do with physics. In 1956, Shockley founded Shockley Semiconductor Laboratory in Mountain View, California, near where he'd grown up. He recruited some of the brightest young scientists and engineers he could find, but Shockley turned out to be a terrible manager, paranoid, controlling, erratic. Within a year, 8 of his best researchers quit in frustration. They became known as the Traitorous 8, and they went on to found Fairchild Semiconductor, which became the seedbed for the entire Silicon Valley ecosystem. 2 of those 8, Robert Noyce and Gordon Moore, would later leave Fairchild to start a little company called Intel, so the semiconductor industry. The personal computer revolution, the entire geography of modern technology. You can trace it back to William Shockley being difficult to work with. History is strange that way. But let's come back to the physics, because the transistor isn't just an engineering achievement, it's a quantum mechanical device through and through. The way electrons move through those doped semiconductor layers, the way the p-n junctions form their depletion zones, the way a small voltage on the base can open or close the flow of current, all of that is governed by quantum mechanics. The band structure, the Fermi level, the tunneling of electrons, the behavior of holes as positive charge carriers. None of it makes sense without the framework that Planck and Einstein and Bohr and Heisenberg and Schrödinger and Pauli built in the first half of the century. The transistor is where quantum theory stopped being philosophy and became infrastructure. And once you have transistors, you can do something extraordinary. You can combine them into logic gates, little circuits that perform basic logical operations. An AND gate, an OR gate, a NOT gate. You feed in electrical signals representing ones and zeros, and the transistors switch on and off to produce an output that follows the rules of Boolean logic. Stack enough of these gates together, and you get circuits that can add numbers. Stack more and you get circuits that can store information, compare values, make decisions. You get a computer. The first computers back in the 1940s used vacuum tubes as their switching elements. Big, hot, fragile. Glass tubes that burned out constantly. ENIAC, one of the earliest general-purpose electronic computers, completed in 1945, used about 18. 000 vacuum tubes and consumed 150 kilowatts of power. It filled an entire room. When transistors replaced vacuum tubes, computers got smaller, faster, cooler, and more reliable almost overnight, and then came the integrated circuit. The idea of putting multiple transistors onto a single piece of semiconductor material. A single chip. Jack Kilby at Texas Instruments and Robert Noyce at Fairchild both came up with this idea independently around 1958 and 1959. And it's what made modern electronics possible. Think about what's happened since then. In 1965, Gordon Moore observed that the number of transistors on a chip seemed to double roughly every 2 years. That observation, which became known as Moore's Law, has held up with remarkable consistency for decades. The processor in your phone today contains something like 15 billion transistors, 15 billion tiny quantum mechanical switches, each one a p-n junction, doing exactly what Bardeen and Brattain demonstrated with gold foil on germanium in 1947, just unimaginably smaller. Modern transistors have features measured in nanometers, billionths of a meter. At that scale, you're dealing with structures that are only a few dozen atoms across. And at that scale, quantum effects don't just underlie the device's operation in some abstract theoretical sense, they become practical engineering challenges. Here's what I mean. When your transistor gate is only a few nanometers thick, electrons can tunnel right through it. Remember tunneling? That quantum mechanical effect where a particle has a probability of passing through a barrier it shouldn't be able to cross. When barriers were thick, tunneling was negligible, a curiosity. But when you shrink everything down to the nanometer scale, tunneling becomes a real problem. Electrons leak through barriers they're supposed to be blocked by. Your transistor that's supposed to be switched off isn't fully off anymore. Current leaks through. That means wasted power, unwanted heat, and eventually errors in computation. This is one of the fundamental reasons Moore's Law has been slowing down in recent years. We're approaching physical limits. Not engineering limits, but limits set by quantum mechanics itself. You can't just keep making transistors smaller forever, because at some point, the quantum effects that make them work in the first place start working against you. The wave nature of electrons, the uncertainty principle, tunneling. These become obstacles rather than tools. And that brings us to something genuinely fascinating, something that flips the whole problem on its head. Because some physicists looked at this situation, quantum effects messing up our classical computers, and asked a remarkable question. What if instead of fighting quantum mechanics, we built a computer that used quantum mechanics as its operating principle? What if the weirdness wasn't a bug but a feature? That idea, the quantum computer, has roots that go back to the early 1980s, and the person who first articulated it clearly was someone we haven't talked about yet. Someone whose personality was as outsized and unconventional as any figure in this whole story. His name was Richard Feynman. And in 1981, at a conference at MIT, he gave a talk that planted the seed for an entirely new kind of computation. Feynman pointed out something that sounds obvious once you hear it, but that nobody had really taken seriously before. He said, look, if nature is fundamentally quantum mechanical, if particles exist in superposition, if they're entangled, if their behavior is probabilistic, then simulating nature on a classical computer is inherently inefficient. A classical computer has to track every possible state of a quantum system separately, and the number of states grows exponentially. For even a modest quantum system, say a few dozen interacting particles, the computation becomes impossibly large for any classical machine. But a quantum computer, one that itself operates on quantum principles, could simulate quantum systems naturally and efficiently. Feynman wasn't proposing a specific design. He was pointing at a horizon and saying there's something important over there. The actual theoretical framework for quantum computing came a few years later from people like David Deutsch at Oxford, who in 1985 described a universal quantum computer, a theoretical machine that could simulate any physical process. And then in the 1990s, things got really exciting, because a mathematician at Bell Labs, yes, Bell Labs again, the same place where the transistor was born, a mathematician named Peter Shor, discovered something that made governments and banks and intelligence agencies sit up very straight in their chairs. He found an algorithm now called Shor's algorithm that could factor large numbers exponentially faster on a quantum computer than any known method on a classical one. And factoring large numbers is precisely the mathematical problem that underlies most of modern encryption, RSA encryption. The system that secures your bank transactions, your emails, your medical records. It all relies on the assumption that factoring a very large number into its prime components is practically impossible for any computer in any reasonable amount of time. Shor's algorithm said not if the computer is quantum. That was 1994. And suddenly quantum computing wasn't just a theoretical curiosity anymore. It was a potential threat to global security infrastructure, and simultaneously a potential tool of extraordinary power. But building an actual quantum computer, that's a whole different challenge from writing algorithms, for one. Because here's the thing about quantum states. They're incredibly fragile. Remember how we talked about superposition? How a quantum system can exist in multiple states at once until it's measured. Well, the environment is constantly measuring things. Every stray photon, every vibration, every tiny thermal fluctuation can cause a quantum state to decohere, to collapse out of its delicate superposition and become just an ordinary classical state. And once that happens, you've lost the quantum advantage. So building a quantum computer means finding a way to maintain quantum coherence, to keep your quantum bits, your qubits, in their superposition states long enough to actually perform a computation. And that is extraordinarily difficult. It's why most current quantum computers operate at temperatures colder than outer space, just fractions of a degree above absolute zero. Inside elaborate refrigeration systems called dilution refrigerators. At those temperatures, thermal vibrations are minimized and quantum states can survive a little longer. But even then, coherence times are measured in microseconds, maybe milliseconds for the best systems. Every operation you perform has to happen within that tiny window before decoherence ruins everything. And this is where we are right now in the 2020s. In this fascinating, frustrating middle period, where quantum computers exist but aren't yet powerful or reliable enough to outperform classical computers on most practical problems. Companies like IBM, Google, and startups like IonQ and Rigetti are building machines with dozens or hundreds of qubits. But the error rates are still high, and the coherence times are still short. In 2019, Google claimed to have achieved what they called quantum supremacy. Their 53-qubit processor, called Sycamore, performed a specific calculation in about 200 seconds that they estimated would take the most powerful classical supercomputer roughly 10,000 years. IBM disputed that claim, arguing that with clever classical techniques, the supercomputer could do it much faster. The debate continues. But the trajectory is clear, and the engineering challenges that remain are some of the most fascinating problems in all of engineering. Think about what it takes to actually build one of these machines. You need to create a physical system where individual quantum states can be precisely controlled, manipulated, and read out, all while being perfectly isolated from the outside world. And there are several very different approaches people are trying, each with its own advantages and its own headaches. The one you've probably heard the most about is superconducting qubits, which is the approach Google and IBM use. These are tiny circuits made from superconducting materials, usually aluminum, on a silicon chip cooled to about 15 millikelvin. That's 15 thousandths of a degree above absolute zero. At those temperatures, the electrical resistance of the circuit drops to zero, and the circuit starts behaving quantum mechanically. You can create a qubit by building what's called a Josephson junction, which is basically two superconducting electrodes separated by an incredibly thin insulating barrier. Just a nanometer or two thick, electrons tunnel through that barrier. There's our old friend quantum tunneling again. And the resulting current can exist in a superposition of flowing clockwise and counterclockwise simultaneously. That's your 0 and 1 at the same time. It's elegant in principle. But the engineering is brutal. Every one of those junctions has to be fabricated with extraordinary precision. The whole chip has to be wired up with microwave control lines that can send precisely shaped pulses to manipulate individual qubits. And the entire apparatus sits inside one of those dilution refrigerators, which looks like a chandelier of gold-plated copper plates and tubes hanging in a vacuum chamber. using a mixture of helium-3 and helium-4 to achieve those absurdly low temperatures. But superconducting qubits aren't the only game in town. There's a completely different approach using trapped ions. Individual atoms stripped of an electron so they carry an electric charge. Suspended in electromagnetic fields inside a vacuum chamber. Companies like IonQ and Quantinuum are pursuing this. The idea is beautiful. You take something like a ytterbium ion or a barium ion, and you trap it using oscillating electric fields, holding it in place like a marble sitting at the bottom of a bowl. Then you use precisely tuned laser beams to manipulate the quantum state of the ion's electrons. The energy levels of the electrons serve as your 0 and 1. And the laser can put the ion into a superposition of those levels. To entangle two ions, you use the fact that they're sitting near each other in the same trap, connected by their mutual electric repulsion. If you nudge one ion with a laser, the vibration passes through the chain of ions like a wave through a string of beads. And you can use that shared motion to create entanglement between ions that aren't even directly adjacent. The beautiful thing about trapped ions is that they have much longer coherence times than superconducting qubits, sometimes seconds or even minutes instead of microseconds. And the gate fidelities, meaning how accurately you can perform operations, tend to be very high. The downside is speed. Operations on trapped ions are slower. And scaling up to large numbers of qubits is tricky because you need to manage all those laser beams and keep all those ions precisely controlled. And then there's a third approach that's even more exotic. Microsoft has been betting on something called topological qubits, based on strange quasi-particles called non-abelian anyons. The idea here is almost science fiction. In certain materials, under certain conditions, the collective behavior of many electrons can create emergent particles that don't exist anywhere else in nature. Particles that remember when they've been braided around each other. You could encode quantum information in the braiding pattern of these quasi-particles. And because the information is stored in the topology, the overall shape of the braid, rather than any local property, it would be inherently protected from local disturbances. Decoherence would be dramatically reduced because you'd have to undo the entire braid to destroy the information. It's a gorgeous theoretical idea. The problem is that actually creating and controlling these exotic quasi-particles has proven incredibly difficult. Microsoft announced progress in 2023 with what they described as a topological qubit. But the field is still in its early stages. It's a long bet. But if it works, it could leapfrog the other approaches entirely. Now here's the thing that ties all of these approaches together. And it's one of the most important ideas in quantum computing today: quantum error correction. Because no matter which physical system you use, errors are going to happen. Qubits will decohere. Gates will be slightly imprecise. Measurements will occasionally give wrong answers. And in a classical computer, error correction is straightforward. You just copy the bit. Store 3 copies of every bit. And if one flips, the majority rules. But in quantum computing, you can't copy a qubit. There's actually a theorem about this called the no-cloning theorem. And it follows directly from the linearity of quantum mechanics. You literally cannot make an identical copy of an unknown quantum state. So quantum error correction has to work differently. And the solution that theorists came up with is remarkable. The idea, developed in the mid-1990s by people like Peter Shor and Andrew Steen, is to spread the information of one logical qubit across many physical qubits in an entangled state. You don't copy the quantum state. Instead, you encode it redundantly using entanglement. If an error affects one physical qubit, you can detect and correct it without ever directly measuring the logical qubit, without collapsing its superposition. The catch is that you need a lot of physical qubits to make one reliable logical qubit. Current estimates suggest you might need somewhere between 1,000 and 10,000 physical qubits to create a single error-corrected logical qubit. depending on the error rates of your hardware. So when someone says we need a 1,000,000-qubit quantum computer to do useful chemistry simulations, what they really mean is we need 1,000 logical qubits, each made of 1,000 or more physical qubits. And this is why the race right now isn't just about building more qubits. It's about building better qubits. Reducing error rates is arguably more important than increasing qubit counts. In 2023, Google published results showing they could make their error-corrected logical qubits perform better as they added more physical qubits, which might sound obvious, but it's actually a crucial threshold. It means the error correction is actually working. The additional qubits are helping more than they're hurting. That's a milestone the field had been working toward for years. So what would a fully error-corrected large-scale quantum computer actually be good for? Let's come back to that, because it matters. The hype around quantum computing sometimes makes it sound like these machines will replace your laptop. And that's just not how it works. Quantum computers are not faster at everything. For most everyday tasks, browsing the web, writing documents, watching videos, a classical computer will always be better. Quantum computers are specialists. They're extraordinarily good at a specific class of problems that have a particular mathematical structure. The most famous, of course, is Shor's algorithm for factoring large numbers, which would break the RSA encryption that secures most of the internet's communications. And governments and companies are taking that threat seriously. There's already a major effort underway to develop post-quantum cryptography. New encryption methods based on mathematical problems that are hard even for quantum computers. The U.S. National Institute of Standards and Technology finalized its first set of post-quantum cryptographic standards in 2024. The transition is happening now, years before a quantum computer capable of breaking RSA is expected to exist, because the threat is that significant. But cryptography breaking is almost the least interesting application. The one that really excites scientists is simulating quantum systems themselves. Which brings us full circle to Feynman's original insight. Think about drug discovery. When a pharmaceutical company wants to understand how a potential drug molecule interacts with a protein in your body, they need to simulate the quantum behavior of electrons in those molecules. And the computational cost of doing that on a classical computer scales exponentially with the number of electrons involved. A molecule with just a few dozen electrons can already push the limits of the world's most powerful supercomputers. But a quantum computer could simulate those quantum interactions naturally, because it is itself a quantum system. The same is true for designing new materials, better batteries, better solar cells, better catalysts for industrial chemistry, new superconductors. These are all problems where quantum mechanics is the bottleneck, where the thing you need to simulate is inherently quantum mechanical, and where a quantum computer would have a fundamental advantage. There's also optimization, finding the best solution among an astronomically large number of possibilities. Logistics, financial modeling, machine learning, scheduling. Quantum algorithms like the Quantum Approximate Optimization Algorithm, or QAOA, might offer speed-ups for certain types of these problems, though the exact advantage is still being worked out. And here's something that doesn't get talked about enough. Quantum computing has already changed how we think, even before the machines are fully built. The theoretical framework developed for quantum information science has fed back into physics itself, giving us new tools for understanding black holes, the nature of space-time, and the deepest questions in fundamental physics. There's a whole field now. It goes by names like IT from qubit, exploring the idea that space-time itself might emerge from quantum entanglement, that the fabric of the universe might be in some deep sense a quantum information structure. It's speculative. And it's mind-bending. And it connects back to everything we've been talking about tonight. Superposition, entanglement, measurement. The strange rules that govern the smallest things in the universe, somehow reaching up to shape the largest. But quantum computing isn't the only place where quantum physics has transformed the modern world in ways you interact with every day without thinking about it. There's another whole category of quantum technology that's already mature, already deployed, already woven into the infrastructure of civilization. And it starts with something deceptively simple: the ability to measure time with extraordinary precision. And I mean extraordinary. The kind of precision that would have seemed like magic to any physicist 100 years ago. So let's talk about atomic clocks. You've probably heard the term. Maybe vaguely associated it with GPS satellites or some laboratory somewhere. But here's what's actually happening inside one. Remember way back when we talked about how atoms absorb and emit photons at very specific frequencies? How an electron in an atom can only jump between certain energy levels? And each jump corresponds to a photon of a very particular wavelength? Well, that property, that absolute unwavering consistency of atomic transitions, turns out to be the most reliable clock in the universe. Every cesium-133 atom in existence anywhere in the cosmos has an electron transition that oscillates at exactly 9,192,631,770 cycles per second. Not approximately, exactly. That number isn't measured against some other standard. Since 1967, that number is the standard. It's literally the definition of a second. 1 second is 9,192,631,770 oscillations of the cesium-133 hyperfine transition. We defined our fundamental unit of time in terms of a quantum mechanical property of an atom, because nothing else in nature is that reliable. And the clocks built around this principle are astonishingly accurate. Modern cesium fountain clocks like the ones at the National Institute of Standards and Technology in Boulder, Colorado, or at the Physikalische Technische Reichsanstalt in Germany are accurate to about 1 second in 300 million years. Think about that. If you'd started one of these clocks when the dinosaurs went extinct 66 million years ago, it would still be accurate today. It wouldn't have drifted by even a full second. But here's what's really wild. Cesium clocks aren't even the best we can do anymore. The latest generation of atomic clocks use optical transitions instead of microwave ones. These are sometimes called optical lattice clocks or optical ion clocks, and they work on the same basic principle, counting the oscillations of an atomic transition. But the transitions they use oscillate at optical frequencies, which are hundreds of thousands of times faster than the microwave frequency of cesium. More oscillations per second means you can slice time into finer pieces, which means better precision. The best optical clocks right now, as of the mid-2020s, are accurate to about 1 second in 15 billion years. That's longer than the current age of the universe. If you'd started one at the Big Bang, it would still be on time. Now you might be thinking, okay, that's impressive, but who actually needs to know what time it is that accurately? And the answer is you do. Every single day. Because GPS, the Global Positioning System, runs on atomic clocks, and your phone uses GPS constantly. Here's how it works. Each GPS satellite carries atomic clocks, and it continuously broadcasts a signal that basically says, I'm satellite number such and such. And the time right now is this. Your phone picks up signals from multiple satellites. And because it knows exactly when each signal was sent and how long it took to arrive, it can calculate how far away each satellite is. And from those distances, it triangulates your position. But here's the thing. The speed of light is about 300,000 kilometers per second, which means a timing error of just 1 microsecond, 1/1,000,000th of a second, translates to a position error of about 300 meters. If the clocks on GPS satellites drifted by even a few microseconds per day, the whole system would be useless within hours. Your Maps app would tell you you're in the wrong neighborhood. Planes couldn't land using GPS guidance. The precision agriculture systems that modern farming depends on would fall apart. Military operations, financial trading, timestamps, power grid synchronization, telecommunications. All of it depends on atomic clocks keeping time with quantum mechanical precision. And here's a beautiful detail that ties together several things we've talked about tonight. GPS has to account for both special and general relativity. The satellites are moving fast relative to you, which means special relativity says their clocks should tick slightly slower, by about 7 microseconds per day. But they're also higher up in Earth's gravitational field, which means general relativity says their clocks should tick slightly faster, by about 45 microseconds per day. The net effect is that satellite clocks run about 38 microseconds per day fast compared to clocks on the ground. If you didn't correct for this, GPS positions would drift by about 10 kilometers per day. So every GPS satellite has its clock rate deliberately set slightly slow before launch to compensate for the relativistic effects it'll experience in orbit. Quantum mechanics gives us the clock. Relativity tells us how to correct it. And the result is that you can find the nearest coffee shop on your phone to a few meters. That's the real world running on physics that seemed purely abstract when Einstein and Bohr were arguing about it in the 1920s. Let's talk about another quantum technology you use every day. Lasers. The word laser is actually an acronym. Light amplification by stimulated emission of radiation. And that phrase, stimulated emission, takes us right back to Einstein, to a paper he wrote in 1917. He showed that there were actually 2 ways an atom could emit a photon. One was spontaneous emission. An excited electron just drops to a lower energy level on its own and releases a photon. That's how most light sources work. It's random. And the photons come out in all different directions with slightly different phases and sometimes slightly different frequencies. That's why light from a light bulb or a candle is incoherent. The photons are a jumbled mess, like a crowd of people all talking at once. But Einstein predicted a second process. If a photon of exactly the right frequency passes by an atom that's already in an excited state, it can stimulate that atom to emit its photon right then and there. And the emitted photon comes out as an exact copy of the one that triggered it. Same frequency, same direction, same phase. Now you have 2 identical photons traveling together. And if those 2 photons encounter more excited atoms, they each trigger another emission, and now you have 4 identical photons, then 8, then 16. It's a chain reaction of perfectly identical light. That's what a laser is. A device that creates a population of excited atoms, and then lets stimulated emission cascade through them, producing a beam of light where all the photons are marching in perfect lockstep. Coherent light. And that coherence is what makes laser light so special. It can be focused to an incredibly tiny point. It can travel enormous distances without spreading out much. And it can carry information with extraordinary fidelity. The first working laser was built in 1960 by Theodore Maiman at Hughes Research Laboratories in Malibu, California, using a synthetic ruby crystal. And famously at the time, people called it a solution looking for a problem. Nobody was quite sure what you'd actually do with it, which is kind of hilarious in retrospect, because today lasers are everywhere. Every fiber optic cable carrying internet traffic uses lasers to encode data as pulses of light. That's how the vast majority of the world's data moves. Every barcode scanner in every grocery store uses a laser. Laser surgery reshapes corneas and removes tumors. Laser cutting and welding are fundamental to manufacturing. CDs, DVDs, and Blu-ray players all read data with lasers. The laser pointers people use in presentations. The LiDAR sensors in self-driving cars. The rangefinders used in construction and surveying. The interferometers that detected gravitational waves at LIGO. All lasers. All based on stimulated emission. A quantum mechanical process that Einstein predicted on paper 43 years before anyone built one. And speaking of LIGO, that's worth lingering on for a moment, because it's one of the most astonishing measurement achievements in human history. And it's quantum mechanical at its core. LIGO stands for the Laser Interferometer Gravitational Wave Observatory. It consists of 2 enormous L-shaped detectors, one in Hanford, Washington, and one in Livingston, Louisiana. Each arm of each detector is 4 kilometers long. A laser beam is split and sent down both arms, bounces off mirrors at the far ends, and recombines. If a gravitational wave passes through, a ripple in spacetime itself caused by something like two black holes colliding a billion light-years away, it stretches one arm and compresses the other by an almost inconceivably tiny amount. How tiny? LIGO can detect a change in the length of its 4-kilometer arms of about 1/10 billionth the diameter of a proton. That's a measurement precision of roughly 1 part in 10 to the 21st power, and the device that makes this possible is a laser interferometer, quantum mechanics providing both the coherent light source and the theoretical framework for understanding what happens when that light interacts with the mirrors, which themselves must be isolated from quantum noise. In fact, the latest upgrades to LIGO actually use squeezed quantum states of light to push past what's called the standard quantum limit, a noise floor that comes from the Heisenberg uncertainty principle itself. They're literally engineering around the uncertainty principle, using quantum entanglement between photons to reduce noise in one variable at the cost of increased noise in another variable they don't care about. It's uncertainty principle judo. And it works. It makes the detector more sensitive, quantum mechanics setting the limit, and quantum mechanics providing the trick to get past it. There's something deeply satisfying about all of this. If you step back and look at the arc of the whole story, it started with a puzzle about hot objects glowing. The black-body radiation problem that Max Planck reluctantly solved in 1900 by introducing energy quanta, a mathematical trick he didn't even fully believe in. Then Einstein took it seriously and said light really does come in packets. And everyone thought he was wrong about that too. Then Bohr built an atomic model that worked, but nobody could explain why. Then de Broglie said particles are waves, and Schrödinger wrote down the wave equation. And Born said the wave is probability. And Heisenberg said you can't know everything at once. And Dirac unified it all into a beautiful mathematical framework. And then for decades, the philosophical arguments about measurement, about reality, about what quantum mechanics actually means seemed like just that. Philosophy. Interesting but impractical. Einstein and Bohr arguing about thought experiments that could never be tested. But then Bell came along and showed that the argument could be tested, and Aspect and others tested it. And quantum mechanics won every single time. And the useless philosophical puzzles about entanglement and superposition turned out to be the key to entirely new technologies. Quantum computing, quantum cryptography, quantum sensing. The things that seemed most abstract turned out to be most practical. That happens a lot in physics, actually. It's almost a rule. The more fundamental and abstract the discovery seems at first, the more transformative its applications turn out to be, given enough time. And now here you are, lying in the dark. And the room around you is full of quantum mechanics. The semiconductor chips in your phone, designed using band theory and quantum tunneling. The LED, or OLED display you were probably looking at earlier tonight, which works because of quantum mechanical transitions in carefully engineered materials. The Wi-Fi signals passing through your walls carried on electromagnetic waves whose nature was clarified by quantum electrodynamics, the MRI machine at your local hospital, which works by manipulating the quantum spin of hydrogen nuclei in your body, the smoke detector on your ceiling, if it's the ionization type, which uses americium-241 undergoing quantum mechanical alpha decay, the flash memory storing your photos, which writes data by quantum tunneling electrons through an insulating barrier. Quantum mechanics isn't some exotic, far-off thing. It's the operating system of reality. It's running right now in every atom of your body, in every photon of light, in every electron flowing through every wire. The rules are strange. Superposition, entanglement, uncertainty, wave-particle duality, quantized energy levels. And after more than a century, we still argue about what they mean at the deepest level. We still don't have a single agreed-upon interpretation of quantum mechanics. Copenhagen. Many worlds. pilot wave, relational, cubism. Smart people disagree passionately. And that's actually okay. The math works. The predictions are confirmed to more decimal places than any other theory in the history of science. Quantum electrodynamics predicts the magnetic moment of the electron to an accuracy of about 1 part in 10 trillion. That's like predicting the distance from New York to Los Angeles to within the width of a human hair. We know how to use the theory, we know how to build with it, we're still figuring out how to understand it. And maybe that's the most honest thing you can say about quantum physics. It gives us answers that work, wrapped in mysteries that remain. The universe doesn't owe us an intuitive picture. It doesn't have to make sense in terms of everyday experience. It just has to be consistent. And it is, wildly, beautifully, maddeningly consistent. So as you lie there feeling the weight of the blankets, letting your breathing slow, here's maybe the most comforting thought in all of physics. Every atom in your body was forged in the heart of a star through quantum mechanical processes. Nuclear fusion. Quantum tunneling allowing protons to overcome their electromagnetic repulsion and fuse together at temperatures that classical physics said shouldn't be enough. The carbon in your bones, the oxygen in your lungs, the iron in your blood, all of it was made possible by quantum tunneling in stellar cores. You are in a very literal and precise sense a quantum mechanical phenomenon. The same strange rules that puzzled Planck and Einstein and Bohr and Heisenberg. The rules we've been talking about all this time, those are the rules that built you. Every atom, every molecule, every cell. And right now, those atoms are doing what they've always done, following the quiet, probabilistic, deeply strange laws of quantum mechanics. Electrons are orbiting in their clouds of probability. Photons are being absorbed and emitted. Chemical bonds are holding your molecules together through quantum mechanical electron sharing. It's all happening effortlessly. The way it's been happening since long before anyone was around to wonder about it. The universe figured out quantum mechanics about 14 billion years before we did. We're just the part of the universe that finally noticed. And now you know a little more about what it noticed, and why it matters. And how a century of brilliant, stubborn, sometimes wrong, sometimes lucky people slowly pulled back the curtain on the strangest and most fundamental layer of reality. That's a good thing to carry into sleep. The knowledge that the world is stranger and more wonderful than it appears, and that understanding it, even a little, is one of the finest things a human mind can do. So let that settle, let the ideas drift, and let the quantum mechanical processes in your neurons do what they do, carrying you gently, reliably, into wherever dreams are waiting. The truth is, we live in a cosmos that's far more beautiful than our ancestors could have imagined, not because it matches our intuitions, but precisely because it doesn't. The weirdness is the wonder.